So, hello everyone. I am Tom Waknine, and I will talk with you about reduction of learning problems in Euclidean spaces. This is based on a joint work with Shai Moran, my advisor, and Bogdan Chornomaz. Okay, so let's start. So our sort of motivation is studying learning via stochastic context optimization. So you start with some samples of points, s of xi, the points, and yi, their labels, and you sort of want to use this sample to generalize to the general learning rule. And the process you use to do it is you take the sample and somehow use it to generate some loss function going from some RD to R, some parameter D. And then you optimize this loss function using some optimization algorithm. You find the W star, which is the argument of L. It minimizes L. And somehow you use this W star to generate HW star, which is some hypothesis. And sort of the hope is that this hypothesis is somehow good for the general problem. Yes, this process is essentially a reduction. You start with some classification problem. You want to use this sample to find a function that can pair a new x to its true label y, even if this x and y don't appear in this function, in this sample. And instead of doing this, you solve a different problem. You solve the optimization problem of minimizing this new loss function. And then somehow you go back from the optimal solution to the new problem to a solution to the original problem. Yeah, so this is a reduction. You start with the problem. You start with the problem A, you somehow uh, transform the problem A into a problem B. You use an algorithm for B to find a solution for B, and then somehow you transform the solution of B to a solution of A. And you want that this diagram will be commutative, like you start with an instance A, you solve it, you transform it, you solve the new problem, you go back and you get a solution to the original instance, yes? So this is like the essential idea of reductions. And we sort of want to study when can you reduce a classification problem to stochastic optimization problem and what sort of limitations you get. So, so this is like our approach and our guiding questions. And, and okay, so let's try to maybe formalize this motivation and intuition so everything will be clear and well defined. So what do I mean by a classification problem? So pack learning, we are working in the pack learning settings. So pack classification problem is essentially just a concept class, set of functions from x to, in our case, plus minus 1. And each point in the label domain, each x and y, induced a 0, 1 loss function. Yes, that this 0 and 1 loss function get functions and I would put a number. So the loss of f at the point xy is 0 if f of x is y and 1 if f of x is not y. Yes, if f classify x correctly, then you don't receive a loss. If f does not classify x correctly, you receive a loss of 1. Then each distribution over x cross plus minus 1, yes, a distribution is like the learning problem. You want to learn distribution. You want to output a function that on a new sample from this distribution, if you only see the x, you can also predict the y. So distribution induce a loss function LD, which LD on F is you just sample xy from D, and and you use the loss of f on this random sample point. This is the same as like the probability of misclassification, yes, because for each xy you receive a loss of 1 if you mistake, so the general loss is just like the probability that f of x is not y on a random xy, and this is what we want to minimize. And in general, here we will work in the realizable setting. So we assume that a distribution is realizable if the infimum over all function in the class is 0, yes. So we assume that you can get arbitrarily small loss, and this is our setup. You can of course drop this assumption, then you just try to minimize LD of 0, 1, but in this case you try to make LD of 0, 1 go to 0. Yeah, that so how does the process of learning look like? And also you choose a realizable distribution, yes. So the opt h of d, the infimum over all functions h of the induced loss function is 0. A sample S is drawn from D, yes, so you sample IID n times X and Y from D. The learner receives the sample S, he uses the sample S to construct a function h of S, yes, so a learner is something that receives samples in output functions. And the goal is to minimize the induced loss function of this h of S, where I maybe take expectation of the overall samples, or I want that this thing will be small with high probability with respect to the probability of the sample S. But this is the general idea, yes. You want that as the sample size go to infinity, the expected loss go to 0. And sort of the rates should be uniform overall in this. Like this is the setup of back learning. So maybe a quick example. So we can look on linear classifiers. So our set of points will be Rd, and our functions for each w in Rd will define a function which phi of w at point x will be the sign of the inner product of x and w. So if the inner product between x and w is 1, is greater than 0, the function is 1, otherwise it's minus 1. So it's like a linear classifier because you use w to classify. You can think about the half spaces that w defines. So on one side of the half space, the function is 1, and the other side of the half space, the function is 0. And then you look on the class of all those functions. This a class of a constant class of functions. So this defines a path learning problem, then this path learning problem is learnable. That there are learners that can learn it quite effectively. Now, stochastic convex optimization is sort of very similar. It's essentially the main difference is that now we assume that our loss functions are convex. So I don't assume what they are. They can be any functions they want, but they need to be convex loss function from some convex set W in Rd to 0 infinity. I assume they are positive. Here Z is just some abstract index sets. Yes, the important part is that I have a collection of convex loss functions. And I guess the parameter space W, which is in Rd. And then again, each distribution induces a loss function, LD of W. Now this loss function is convex because it's a convex combination of convex loss functions. So it itself also convex. Again, the adversaries choose the distribution D. This time we don't necessarily assume it's realizable. It's not too important, but like for general convex, false convex optimization, maybe maybe the minimum of LD of W is not zero, but the process behaves the same. You sample point S of n z yes, of n loss functions, and so you sort of get the loss function of the loss on those points. You get those loss functions, and you sort of use them to approximate LD. Yes, you use the sample to generate a point, and you want that this point will minimize LD. Yes, so you get like a sample of those guys, and you want to minimize this guy. So again, an example, this pretty similar example to what we saw before, but now as an SEO problem. So take W to be all of RD, or if you want just stick to the unit pole or something like that. Z will also be RD of plus minus 1. So for each xy, we need to define a convex loss function. So what will be our convex loss functions? So Lx of y at the point W is the maximum between 0 and 1 minus y inner product between W and x. Yes, so you can check this called the hinge loss function. Maybe some of you know it. It's pretty useful. You can check it's convex. So this thing define a convex SEO, a convex stochastic convex optimization problem. So hopefully the setup of path learning and stochastic convex optimization is clear. Now, what do we mean when we say that you can reduce a path classification problem to an optimization problem, a path to SEO? So such reduction from a path to an SEO, it's made of two things. Yes, you need an input map that transform instances to instances. So in our case, we need to transform x cross plus minus 1 to z. Yes, so it's sort of like sending loss functions to loss functions. And you need an output map that for each point W associates some function f of W. Yes, because solution to the SEO problems are W, solutions to the specific functions, we need to always going from W's to functions. And obviously you want the reductions to work, so what it means that reduction is working is that for each realizable D, solving the induced SEO problem will give a solution for D. So induced SEO problem, yes, this guy, so you are these the distributions that sample X cross Y from D. So here you get a sample from here, according to D, and then you use R to send it to point here. So you essentially get a distribution over Z. This is like the push forward map, essentially. So this defines an SEO problem. And then you say that if W solves it, in the sense that it is alpha optimal, it's less for some parameter alpha, then the induced problem, FW, yes, the induced solution, need to solve the original problem, in the sense that it's less than beta. Now, both alpha and beta are some internal parameters. We don't really specify what they are. Obviously, you want beta to be as small as possible, so your reduction will give you the best solutions possible, but our result works for any beta less than half, so I don't really need to specify it, and alpha also, I don't really need to specify it. Our results work for any positive alpha. So it's not really important which numbers you put here and here. Yes, here you want something as small as possible. Here, I guess you want something as large as possible, but like it's not really too important, and don't worry about those guys. The essential idea is that a solution to the SEO problem gives me a solution to the original problem. So let's see an example of a reduction. So recall our previous example of the linear classifier. So the domain was RD, the constant classes were the, which W, you get the function phi of W at X, which is the sign of the inner product between W and X. The zero, the loss function was obviously the zero one loss functions. Yes, the one if you're mistaken and zero if you label correctly. As an SEO problem, we saw something very similar. The parameter space was R of D, which is already promising, and the sample space was RD cross plus minus one, which is like essentially X cross plus minus one. So this is good. And the loss function was like this int loss function. And then you get like a very natural reduction, like Z is already x cross plus minus 1, so you can just use the identity function that's sending xy to xy, and transforming parameters in W to function, you're doing the obvious way, W goes to phi of W, yes, the functions are already parameterized by W, so this is sort of like the obvious thing to do, and you can check that this is turn out to be a reduction under our formal definition of reduction. So this is good news. Because if this wasn't a reduction, then your definition is probably a bad definition. But this works out fine. Okay, so now let me describe the main result. So main result relates the reduction of back to SEO via the VC dimension. I don't really want to go into VC theory too much. So if you know what the VC dimension is, this is good. Yeah, we have the definition for refreshing. If not, don't worry about it too much. Yeah, just know it's an important parameter in learning theory. You have the VC dimension. You also have the dual VC dimension, which is like the VC dimension of the dual class. Dual class, you swap the role of x and the h. So your functions are parameterized by the point x, and their input is functions h, and the point x at functions h give you h of x. This is like this transformation, but this thing is not too important. Like just know that you use this parameter, which is very standard and very fundamental in learning theory, so it makes a lot of sense to look how does this VC dimension relate to any parameter you study, and in our case, the those reductions. So what we need to know about the VC dimension, so a class is learnable if and only if it has a finite VC dimension. The optimum information theoretic optimal learning rate is VC of h over n, where n is the sample size. So the error you get is VCH over n when you use n samples. Sometimes people use the heuristic that the VC is like the number of parameters. So for example, in the half spaces, like the number of parameters is obviously D because you have like D coordinates, and the VC dimension is D plus one. And in a lot of other cases, you get this like sort of polynomial relation between the VC and the number of parameters. This heuristic doesn't work in general. There are some weird cases where the class can have a single parameter, but in VC dimension, like this class right here that has a single parameter t, and for each t you look at the function that sends x to the sine of sinus of t, of tx. You can also find other examples, but it's not very important, just like know that this heuristic is not perfect. Although our result is sort of maybe can make it something more formal and more exact. The VC dimension and the VC dual dimension are finite together, but they can have an exponential gap. Yes, the VC can be is less than VC to VC star and more than log VC star, and those bounds are tight. So this is essentially everything you should keep in mind on the VC dimension. If you don't know it, if you know it, then excellent. And now let's state the main result. So our main result is if you have a concept class H, and you have a reduction of this concept class to some parameter space in RD, yes, so W is in RD, or your convex loss functions are in RD, then this D's must be at least the VC dimension and the VC star dimension minus this minus one, but essentially you get a bound on the dimension to which you can find an SEO reduction. Yes, obviously you want to reduce to as low dimension as possible, because all your stochastic concept optimization algorithm, the higher the dimension are, the more complicated the space is, the space complexity grow higher, and like the stuff gets more complicated when you go to higher dimension. So you want to find like as low dimension as possible, but you can't find like arbitrary low dimension. You get this bound of both VC and maybe surprisingly VC star. I think it wasn't really expected to appear in this context, but it does. Yes, also you can obviously define like the SEO dimension or concept class, or like the smallest d, to which you can find a reduction of h into a d-dimensional SEO problem, and then this theorem is essentially telling you that this dimension is bounded below by VC and VC star. We don't know how to bind this SEO from above by a function of the VC. If it can be done, I think it will be very interesting. It will have some other consequences. But right now, we don't really know how to approach this. And I guess like the corollary of this result is like you have some concept classes which are simple to learn, in the sense that they have low VC dimension. The VC dimension is like log of D. Well, they are complicated to learn via stochastic convex optimization, in the sense that their SEO dimension is D. So you can think about D as something very large. So log of D is small, so we can learn H in a simple way, but the SEO dimension is very large. So if I want to parameterize it, I need a lot of parameters. So I guess it's sort of show you that there is also like a higher another barrier besides the VC dimension of using this approach of reducing parameterizing the problem. And this separation is actually witnessed by a very simple and natural concept class. Yes, it's not like a weird counterexample like what we had before with the sinus of the sine of the x. It's like something very natural and very useful that appear in a lot of cases. And that's it. I hope the result itself is clear. I'm not going to talk about the proof at all, although the proof is, in my opinion, quite interesting. It uses some topological tools, but this is everything I wanted to talk about. So thank you very much, and hopefully you enjoyed the talk.